What is going on, everyone? Welcome back to another video. Today we're going to be doing a steady state thermal analysis, conduction through a composite wall. Let's get into it. So what is thermal conduction? Well, I presented a similar slide to this in a previous video where we did thermal conduction through one wall, and we saw that thermal conduction was the transfer of heat energy within a material that was a solid or between materials that were within direct contact with one another, which we are going to see in this video. And this heat transfer was resultant of collisions and the movement of particles that were transferring kinetic energy between each other upon heating. The rate of thermal conductivity depended on the thermal conductivity K, which was a material specific quantity. And we're going to see how different materials will affect the transfer of heat through a composite wall in this simulation. Now, as I presented before, the governing equations for this problem is Fourier's law, which says that the total heat flux is equal to the negative of the thermal conductivity times the area times the temperature gradient over the wall, which for a linear distribution is simply the difference in temperature over the wall divided by the length or thickness of that wall. And we can rewrite Fourier's law in order to make the total heat flux through the wall analogous to an electrical system where we get thermal resistance is equal to the length divided by the thermal conductivity times the area, since the thermal conductivity is what is resisting the heat transfer through the wall or the heat flux from moving through the wall thickness. So as we can see in the image up here, when we have multiple panels of walls of different materials stacked up against one another, we can rewrite this whole system as a simple electrical system that is represented by resistors in series with one another. So if we wanted to find the total heat flux across this entire wall, we could go ahead and take the temperature at the end over here, Tn, subtracted by the first temperature, T1, and divide the difference in temperature by the total resistance, which is simply the addition of each of the thermal resistances for each segment of wall if they are in series with one another. In the event that we had a wall segment that had two different materials stacked on top of one another, well, then we could represent this system as an electrical system that had two resistors in parallel with one another. And unlike in series, where we can add the resistances to one another to get the total resistance, we would have to use the formula here in order to get the total resistance for the resistances that are in parallel with one another. And then we could add it to the other resistances that are in series with it. However, for this particular problem, we are going to keep it simple. We are going to be doing the thermal conduction through a composite wall. We are going to have 3 plates stacked up against one another, which is analogous to 3 resistors in series with one another. Each plate is going to have a dimension of 1 meter by 1 meter by 0.1 meter. And the temperature at the right boundary over here is going to be 100 degrees Celsius. And the temperature on the left boundary over here is going to be 22 degrees Celsius. And no, we do not need to specify the temperatures in the middle here. Ansys is going to calculate that based on our external boundary conditions and the thermal resistances of each of the plates. Now, the materials for the plates, I have chosen just 3 materials at random from the Ansys Workbench. The first plate is going to be of stainless steel, which has a thermal conductivity of 13.8 watts per meter Kelvin. The middle plate is going to be made of a material of steel 1010, which has a thermal conductivity of 45 watts per meter Kelvin. And then the last plate is going to be structural steel that has a thermal conductivity of 60.5 watts per meter Kelvin. So upon doing this simulation in Ansys, we should see results similar to the image on the right-hand side here, where we have a temperature gradient across the 3 plates respecting the boundary conditions on the left-hand side with a temperature of 22 degrees Celsius and the respecting the temperature at the right-hand side here of 100 degrees Celsius. Furthermore, for result validation, we can go ahead and use Fourier's law to calculate the total heat flux that we are expecting to get through the wall. And this is simply equal to T4, which is the temperature at the right boundary, minus T1, which is the temperature at the left boundary, because in the center here, we would have T2 and T3. And we're going to divide this by the total resistance. And since these plates are in series with one another, the total thermal resistance is simply the summation of each of the thermal resistance of each plate. Now we can calculate the total thermal resistance as follows. And dividing our difference in temperature by the total thermal resistance, we should see that we get a total heat flux through the wall of 713.45 watts. So now that we know the basics of thermal conduction through composite walls, we know what the problem is that we're setting up, and we know the results that we are expecting to obtain in order to validate the results that we get. We can go ahead and jump into Workbench and get started on building this simulation. Now with Workbench open, we can go ahead and start building our simulation. In the middle here, we have our project schematic where we are going to be using different analysis systems to build the simulation. And on the left-hand side here is our toolbox of all the different analysis systems available for us. And the analysis system that we need for the simulation is steady state thermal, so we can drag that into our project schematic. First things first that we need to do is make sure that we have all the materials necessary in order to build the simulation, because by default, Ansys only uses structural steel. So we can double click on engineering data, and this is going to open up a new tab up here. So if we press on the project tab, this brings us back to our project schematic. So in the engineering data tab, if we press on engineering data sources, this opens up the material library of all the different materials that are within Ansys. And I'm going to go ahead and find my steel 1010 and stainless steel material. And when I found these materials before, I found them in the thermal materials library here. So if we click on thermal materials, this will open up the list of materials within this library. If I scroll down to the bottom, I can find here steel 1010. So if I press the plus beside steel 1010, I will add it to my project. And as you can see, we have a little book next to steel 1010 now. So it's been added to our project. And I'm going to do the same thing for stainless steel here. Press on the plus. And if I scroll back down, we can see that we now have a book beside stainless steel. So that's been added to our project. And if we go ahead and press on steel 1010, we can view what the material properties are for this material. We can see that the isentropic thermal conductivity is equal to 45 as we specified in the problem statement. And if we click on stainless steel, we can see that the isentropic thermal conductivity is equal to 13.8 as we specified in the problem statement as well. And if we scroll up, I believe if we go to favorites, we can see structural steel, which is by default in the Ansys project. And so if we click on structural steel, we'll see that the isentropic thermal conductivity is equal to 60.5, which again was specified in the problem statement. So now that we have all the materials that we need in order to build our composite wall with the correct thermal conductivities, we can go ahead and go back to our project tab by pressing on project. And next thing in line is to build our geometry. So let's go ahead and double click on geometry. As we see in the bottom left corner here, it says starting SpaceClaim, so I'll wait for that to load. Now with SpaceClaim open, we can go ahead and start building our geometry. By default, SpaceClaim has us sketching on the ZX plane, but I prefer sketching on the XY plane. It just makes it better for initialization of boundary conditions later on. So I'm going to go ahead and press on Edit Sketch Editing to get to the main environment. And the first thing that we're going to do before we start sketching is ensure that our units will be consistent with the rest of the simulation. By default, Ansys uses meters, seconds, and kilograms. So I'm going to go ahead and ensure that my SpaceClaim environment is also using the same units as that. So I'm going to press on File. Then I'm going to go to SpaceClaim Options, and this is going to open up a window as seen here. I'm going to press on Units. And as we can see, the length currently used is millimeters. I'm going to change this to meters. And the mass here is also in grams. I'm going to change this to kilograms just to make it consistent with the units that we're going to see later on. To confirm these changes, I'm going to go ahead and press on OK. Now we can start sketching our composite wall. So I'm going to go ahead and press on Sketch Mode. And I'm going to select the plane that I want to sketch on. So this is the ZX plane here, and I can select the XY plane by going into this quadrant up here. I'm going to press on the Z axis to make this normal to the screen. I'm going to grab my rectangle command, and I'm going to press at my origin to snap one of the corners of the rectangle to the origin of my environment. And then I'm going to drag out my mouse in order to expand this square. And we can see that we have two dimensioning lines that we can type in the dimensions that we want for our wall. So I'm going to go ahead and type in 1 for 1 meter, press on tab to go to the second dimensioning line. And I'm going to put in another 1 here and then press enter. And then this should give us a 1 by 1 square as shown here. So if we go to end sketch editing, this will create a surface based on the sketch that we provided. And if I use the pull command, as seen up here, I can then pull this wall out and specify this length to be 0.1 meter. Now that we have our 1 by 1 by 0.1 meter wall, we need to add 2 more of them to create our composite wall. There are multiple ways that you can do this, but I think the easiest way to do it is select the surface that we have here, right click and press on copy, and then right click again on the same surface and press on paste. And as you can see in the structure tree here, we've created a surface. So if we deselect the solid that we created earlier, we can see that we have a surface of 1 by 1 meter that is on top of the solid that we constructed. So by using the pull command, if I select the pull command, I can now pull this surface out and specify the thickness to be 0.1 meter. Press on escape. And now I have another wall beside the first wall that we constructed. And I can do the same thing to create my third wall. So I'm going to go ahead and deselect the pull command by pressing on escape. I'm going to press on the surface that I have here, right click, press on copy, right click again, press paste. This created a new surface, as we can see in the structure tree. I'm going to deselect the 2 other solids that I have in order to see the surface. And I'm going to press on the pull command and pull this surface out to give it a thickness of 0.1 meter. Press on escape. And now if I put check marks beside each of these solids, I can see that I have now 3 walls stacked up against each other, each with a thickness of 0.1 meter. Now I can leave this geometry as is, but it's better if we group similar solids together so that when we move on to the meshing stage and the boundary conditions, Ansys doesn't get confused with the material assignment of each of the different solids that are in contact with one another. So to do this, I'm going to go ahead and select all of my solids in my design tree here. So I'm going to press on the first solid. I'm going to hold shift and press on the last solid. So we can see that all of these solids are now selected. I'm going to right click and press on move each to new component. And so now we can see in the design tree, each of our solids is a different component. And this will be easier for Ansys to handle for material assignments and interface purposes. Now, to ensure that the mesh of these 3 different components that are in contact with one another is going to conform, I'm going to go ahead and press on design up here. And in the section here that says shared topology, I'm going to go ahead and press on none in order to get the little drop-down menu here. And I'm going to press on share. And this will just ensure that the mesh is conformal and that we're going to have the same number of elements at the interface of each of these components. So that is it for our geometry. Now we can close SpaceClaim and move on to the meshing stage of this simulation. So I'm going to go ahead and press on the X on SpaceClaim. Now we've returned back to Workbench and we can see that we have a check mark beside geometry, so that is ready to go. So I'll double click on model to move on to the meshing stage and boundary conditions as well. So I'm going to double click on model and we can see down in the bottom left corner, it says starting mechanical. So I'll wait for that to load. So now with mechanical open, we can go ahead and create our mesh, implement our boundary conditions and run the simulation to get our results. But the first thing that we need to do is ensure that our material assignment for each component is correct, because by default, Ansys uses structural steel and assigns each of the components to be made up of structural steel. So to do this, I'm going to go ahead and press on the plus beside geometry. I'm going to press on the plus beside this object here. And now we have each of our components solids of our composite wall. And if I press on the first component, we can see that this is the last component. It highlights this component in our wall. And we can see that this is made of structural steel, so that is good to go. I'm going to press on the second component here, which is our middle plate of our wall. And we can see that the material assignment is also structural steel. If I press on structural steel, we have a little triangle that appears here. If I press on the triangle, it opens up the tree where we have all the materials that we added to our project. And so I'm going to make this material steel 1010. And our third component is the leftmost plate. And again, the material assignment is structural steel. So I can change the material by using the drop-down menu that appears. And I'm going to select stainless steel as the material assignment for the leftmost plate. Now with the material assignment performed, I can go ahead and create the mesh for the simulation. I'm just going to go ahead and generate the default mesh since this is a fairly simple geometry, and I'm going to see what it gives me. So I'm going to right click on mesh and press on generate mesh. And we can see that by default, the mesh that Ansys has created is fairly good, is very orthogonal, and it's not too coarse. So this will actually be a good mesh for this simulation since this is a fairly simple simulation to perform. So now with a good mesh, we can go ahead and add our boundary conditions for this problem. If we right click on steady state thermal, I can insert a temperature. And now by choosing the face selector tool or pressing on Control F, I can press on my leftmost face here. And as you can see, it's been highlighted, so I can go ahead and press on apply on geometry. And by default, it's specifying the temperature to be 22 degrees Celsius. So that is good to go because that was my leftmost boundary condition as we saw in these slides. And I can do the same thing if I right click on steady state thermal, go to insert and insert another temperature using the face selector tool and rotating my wall to the other side, press on the surface and press on apply. And then I change the magnitude of the temperature to 100 to initialize the other boundary condition. So now with my two boundary conditions at play, the 100 degrees Celsius on the rightmost side and the 22 degrees Celsius on the leftmost side, I can go ahead and run the simulation. But before I do that, I want to specify a few results that I want to get from Ansys. The first thing that I'm going to do is right click on solution, go to insert and go to thermal and insert the temperature plot. So this is going to plot the temperature all across my wall. And the other thing that I would like to do is add reaction probes in order to calculate the heat flux across each of these surfaces here. So to do that, I'm going to go ahead and right click again on solution, go to insert, go to probe, and I'm going to add a heat flux probe. Now, Ansys is asking us to specify what the geometry or location of the probe is going to be. So using the face selector tool, I can press on the leftmost face and apply this to my heat flux probe. And we can see that we have a yellow field that has appeared here. This means that Ansys is waiting for user input. So for the results selection, if I press on all and press on the drop-down menu, we can see that we have different options here. I'm going to press on total because I want to get the total heat flux through this surface here. Now that we know how to add a heat flux probe, I can go ahead and also add one for each of the surfaces, including the ones in the center here. And this would be used to ensure or to validate the results to ensure that the heat flux is constant throughout the entire wall. So I'll go ahead and do that. I'll right click on solution, go to insert, go to probe and insert heat flux. Now for the geometry, I want to select the surface that is between these two plates. So to do that, I'll take component 3, which is the leftmost wall. I'll right click and hide body. Now I can select this surface here. So if I go back to heat flux probe, use the face selector tool, press on this face, press on click to change and press on apply. We've now added this surface for our heat flux probe. And in result selection, we'll change this to total to get the total heat flux. I'll do this again for the surface between these two walls. So I'll right click on solution, go to insert, go to probe, go to heat flux. I will press on component 2 and hide this component. I'll click back on heat flux probe to get the details of heat flux probe 3. I'll use the face selector tool, select this face here, click to change, press apply, and then result selection again, drop down menu, press on total, get the total heat flux. And lastly, I'll add one more, go to insert, probe, heat flux, and I'll rotate this to get the outer surface here. Face selector tool, select the surface, press on apply, and results selection changes to total. Great. So now we have a heat flux probe at each of the surfaces of each of the walls in order to see if the heat flux throughout the entire wall stays constant. And before running the simulation, I'm going to go ahead and make sure I can see all the bodies. So I'm going to right click on one of the components and press on show all bodies, and I get all of my bodies showing up again here. So now with the mesh initialized, our boundary conditions in place, and with all the results that we want to see from this simulation, we can go ahead and actually run the simulation. To do this, I'm going to right click on steady state thermal. I'm going to press on solve. As we can see in the bottom left corner here, it is running through the solution right now, and it is ready for viewing. So the first thing that I can do is press on temperature. And I can see that this is my temperature gradient throughout the entire wall. I can press on the little play button here to see the animation with time. But if we analyze these results, we can see that they are fairly good because my temperature gradient across the entire wall is respecting the two boundary conditions that we put into place, 22 degrees Celsius and 100 degrees Celsius on the right-hand side. Lastly, we can press on the heat flux probes to ensure that my heat flux is remaining constant. So on my leftmost wall, we can see that we have a heat flux of 7,013.4 watts per meter squared. And knowing that my area is a 1 meter squared area, it simply gives me a heat flux in total of 7,013.4 watts. And this is consistent with the calculations that we saw in the slides earlier in this video. And if I press on the other heat flux probes, I can see that my heat flux is constant throughout the entire wall. So that is a very good result. So with the results validation completed, we can go ahead and conclude that the simulation was performed with a high degree of accuracy. And that will be it for this video of thermal conduction through a composite wall. I hope you guys thought it was helpful. Don't forget to like the video if you thought it was, and subscribe for more engineering content.